All right, so I've tried to stay a little bit color coordinated with this note. Again, informational. With this note, I've tried to keep 2 space in blue and 3 space in red. So the first thing is we're talking about component form, meaning the square bracket deal, rather than the standard vector basis form that we were talking about. Let me check the exact name of that. Standard basis vectors. So we're not talking about the I, j, and k, even though it can extend itself to that. We're talking about component form. So if you've got a vector in 2 space, if you've got a vector A, which is x1 comma y1 as its components, and a vector B, which is x2 comma y2 components, and I ask you to add them together, you literally have to add the x components together and the y components together, and that gives you vector A plus vector B. In the case of R3, so 3 space, you'll have an x, y, and z. So this time to show the textbooky rule, vector A is x1 comma y1 comma z1 components, plus vector B, I'm saying, is x2, y2, z2 components. To find A plus B, vector A plus vector B, you add the x components, you add the y components, you add the z components, you put commas in between, and still put square brackets around it because they are components. The next thing we'll look at is scalar multiplication, and scalar multiplication is multiplying by a number, like a normal everyday number. So I'm still using vector A, although I could change it to whatever I wanted to, and I'm still using standard, very uncluttery letters, only I don't have an x1 and a y1 this time. I've just got a vector, and I've got a real number, or a scalar, and I'm calling it m. Notice the lack of vector symbol up here. It's because it's a scalar. If I ask you to change or to multiply the scalar by a vector, so m times vector A, what you need to do is you need to take the x component and the y component, and you need to multiply both of them by the m. In the case of R3, where you'd have components x, y, and z for a vector A, and I asked you to find a scalar times a vector, you would have to take the x component and the y component and the z component and multiply each of them by whatever number it is, in this case m, and make sure that it's still in component form. So here's an example. And I think I'm going to try to do 3 space all the way through, because if you can do 3 space, you can automatically do 2 space because it's less of it. So, I'm going to use blue. So 5 vector u means 5 multiplied by component 2, negative 3, 4, component square brackets, plus 7 times v, so components 5, negative 7, negative 3. So the first thing I'm going to do is scalar multiplication. So I have new components of 10, negative 15, and 20, plus, now I multiply the 7 through, so 35, negative 49, negative 21. So that is scalar multiplication. Now to finish this off, I need to do vector addition for 3 space, and vector addition is taking first component plus first component, so 45, second component plus second component, so 59, 64, negative 64, and third component added to third component, and making sure that your answer is in component form because it's still a vector. All right, next set of rules. Magnitudes. So if I ask you for how long a vector is, if I give you a vector A, and in 2 space, so 2 components, and I ask you for the magnitude of vector A, you kind of do the distance formula from grade 10. You kind of do Pythagorean theorem because it's the same thing. So you take the x coordinate component, square it, y component, square it, add them together and square root. And in the case of R3, you take the x component plus squared plus the y component squared plus the z component squared, all under a square root to get the magnitude of vector A. Next informational stuff is components of a vector running between 2 points. So let's say one of your points is not 0, 0, or not 0, 0, 0 in 3 space. If you have a random point out in 2 space, and you've got a random second point in 2 space, and I tell you what the beginning point is, and I tell you what the ending point is, you have to minus ending point minus beginning point components. Ending point minus beginning point. So you have to take this point components minus this point. And the same is true for 3 space, only you do it 3 times. Ending point x component minus beginning point x component. y2 minus y1. z2 minus z1. And your answer is in component form. All right, so here's some examples. So I'm going to move 2 a little bit away so I have some space to think and write. So the first thing I want to do is I want to find vector AB, given that I've got points, C, round brackets. A is 5, negative 9, 4, and B is negative 7, 2, 11. So I'm going to set this up for components because this is a vector, and I have to do ending point minus beginning point. Ending point minus beginning point. Ending point minus beginning point. 11, 7. And there is vector AB. Now, I hope some of you pick up on the fact that what I'm about to do is entirely unnecessary, but this question is asking for the magnitude of vector BA. So the first thing I'm going to do is I'm going to find vector BA. That means I have to do ending point minus beginning point. Ending point minus beginning point. Ending point minus beginning point. So that is 12, negative 11, and negative 7. And I hope some of you realize that it would be the exact opposite of this one because that is the reverse vectors. And we talked about that in geometric vectors. So the length of AB and the length of BA should be exactly the same, vector AB and vector BA. I do want to give you a little tip before we go on and take care of the magnitude, and that is if you struggle with order, which I do, I will take the ending point and the beginning point and list them this way, and then do my subtraction in here, do my subtraction in here, do my subtraction in there, and I am less likely to make dumb mistakes in getting my answer because my order is sort of dictated for me. So now I'm about to do the magnitude of vector BA. So that is going back to this one, which is a longer version of this. So like I said, I'm doing 3 space instead of 2 space because it's longer, so you should be able to shorten things up. So take each component, square it, add it together, and stick it under a square root sign. So sort of Pythagorean theorem on steroids. So 12, and I'm putting everything in a bracket, even though I don't need to, squared plus this one needs to be in a bracket because it's negative, plus this one needs to be in a bracket because it's negative. So that's 144 plus 121 plus 49. You should only end up with positive numbers, and I still have to take the square root. I can't add those numbers in my head. I could if I really wanted to off to the side, but I've got a calculator right here to help me decide if you are going to a school that doesn't let you use a calculator or not. And I end up getting 314 under a square root sign. And if you want to, you can reduced radical form that, and if you want to, you can turn that into a decimal. It doesn't say what to do. I know that some of you have a little bit of struggling with reduced radical form, so I am going to take 314 and divide it by 2, which does not divide by 2 again, so 4 won't work. 314 divided by 9. Nope. 314 divided by 3 times 3, 4 times 4, 16. Not going to work because 2 2's didn't work. 25, no. 36, no, I don't think that's going to work. Might as well try it. 314 divided by 49. Nope. 314 divided by 7 times 7, 8 times 8, 64 won't work. 9 times 9, 81. I don't think this is, I think this is already in reduced radical form, so I'm going to stop there. Again, if you really, really, really want to, and you're totally allowed to do this, you can say that that is approximately equal to 17.7 units. Not sure what the units are. But as soon as you take the square root disappears and you are left with a regular number. All right, next question. I need to find 2 times the vector OA minus 5 times the vector OB. And then once I'm done that, I need to find the magnitude of it all. So the first thing I'm going to do, step 1, is forget about the magnitude and sort of do this in steps, and I'll deal with just that part. So 2 times OA, vector OA is 2 times components 3, negative 7, 4, minus 5 components 6, 3, negative 8. Now I'm going to give you a tip. That was out of habit, which is also something that gets in the way of me because I'm sloppy. So I'm going to take these ones and I'm going to multiply by 2, by 2, by 2. There it is again. What I choose to do personally is I choose to multiply all these by negative 5 and put a plus sign in there. So negative 30, negative 15, positive 40. I choose to do that because I am a better adder than I am a subtractor. So then I can take each individual component and I can add it to its counterpart. So 6 plus negative 30, negative 14 plus negative 15, 8 plus 40. Much better adder. And now I have to find the magnitude of that. So the magnitude of 2 vector OA minus 5 vector OBs is equal to negative 24 squared plus negative 29 squared plus positive 48 squared. I'm going to show all my work. So I know that 24 squared and negative 24 squared are the same thing. That went a little bit haywire. So that's 576 plus, same thing with 29, 841. Not applicable, but same thing for 48. 2,304. And then I have to add all those together. So that's on my calculator still. So plus 841 plus 576 equals, and I get under a square root sign, 3721. And you can reduce radical form that, or use the calculator to find the square root. Ooh, that's pretty. Straight up 61. 61 units long, that vector is. In 3 space. Don't want to draw it. Don't challenge me. All right. After that, I need a little hand cramp break. I will be back in a second. Actually, more than a second. Okay, so I know you've heard me say this before, but I really like this next question. So, what I like about it is that this question is asking for vector B to A. So point B to A, and I don't have a point B and I don't have a point A. I've got a vector OA and I've got a vector OB. And so this might look like it's a bit of a problem, but it's not. Because OA, and we'll talk about that only because the whole thing is exactly the same for O to B. Vector OA is created by subtracting, and I can't remember where I put it, so give me a sec. I think it's in the last note, which I actually didn't get rid of. No, it's in this one. Oh, maybe it is in the last one. Watch me struggle. Nope, it's in this one. Where is it? Oh, there. So, if you've got 2 points and you're asked for a vector between those 2 points, you have to subtract end minus beginning. So I always say subtract backwards. So you put the B on top in my strategy and the A on the bottom. So in this particular case, erasing ahead a little bit, in this particular case, 3, -7, 4, I would have been asking you to take 3, -7, 4, point A, and point O, which is 0, 0, 0, subtract, subtract, subtract to create this vector. And the same thing with this one. So really, we know that vector OA has components 3, 7, -7, 4, but we also know that A has coordinates 3, -7, 4. It also means that B has coordinates, so point B has coordinates 6, 3, -8. And notice how I arranged them on my page. I put the last one first and the first one second, and now I have to do some subtraction. So that's 3 minus 6, -7 minus 3, 4 minus -8. So to find this vector, I subtracted, and I'll get my 3 components, and we're done. So I really like that question because it makes you think about what you know versus what you need in a question. All right, now the slide I accidentally previewed, and that is a unit vector. So we talked about unit vectors briefly in geometric vectors as opposed to Cartesian vectors. The formula back in the last unit is the same as the formula here. So it's 1 over the magnitude of the vector multiplied by the vector. So this is a scalar and this is a vector. So if you're in 2 space, That means you have 1 over, here's your magnitude formula, multiplied by the 2 components. And if you want to, you can write it like this, meaning that it's x multiplied by 1 still over the magnitude, and y multiplied by 1 still over the magnitude. And then in 3 space, it's exactly the same, so the formula does not change, the main formula, but the magnitude and the amount of work is 1 more component's worth. So here's our last question for today, and that is, given that we have a vector q with components -2, 4, and -7, determine a unit vector in the same direction as q. So the first thing I'm going to do is I'm going to find the magnitude of q, because I need that whether I'm in 2 space or 3 space. So I have to take -2 and square it, plus 4 and square it, plus -7 and square it. So that's 4 plus 16 plus 49, all under a square root sign. So it's 20, so it's 69 underneath a square root sign. And it is late, so don't carve me up about this. So I can't divide by 9. I can't divide by 4. I can't divide by 16. So that's in reduced radical form already. Next thing, so that's step 1. I like to do things in steps rather than the whole massive formula at exactly the same time. I'm going to change colors for fun. And so the unit vector will be 1 over the square root of 69 times components -2, 4, -7. And you could write that as in -2 over the square root of 69, +4 over the square root of 69, comma -7 over the square root of 69 in component form. So if it's 2 space, you have 1 less calculation. But it's not 2 space, it's 3 space, so I have to keep it 3 space. So that is something that you do need to keep in mind, is that 3 space is always 3 space and 2 space is always 2 space. And square brackets are always square and round brackets are always round. Now, this is a unit vector in the same direction as vector q. But there's this teeny little question that I slid in there about what about a unit vector in the opposite direction to q? And the answer for that is simple. As in, the calculation is simple. In the opposite direction to q. No new calculations necessary. What is necessary is carefulness, if that's a word. So not -2 over root 69, but +2 over root 69. Not +4, -4 over root 69. Not -7, +7 over root 69. So it's the exact opposite signs from the original. You cannot miss one, otherwise you're wrong. And you also have to put square brackets around it because it is still a vector. All right, so these calculations are here. So again, R2 in R2 and R3 in R3. So you have lots of places to practice that kind of stuff. So that is informational note number 2.